And now in this lecture we'll answer on two questions. In the first question we find out the area of this green shape, and in the second question we find out the length of line segment AP is equals to x using two different methods. So we start with the first question. In the drawing we have a semicircle. We know that chord PC equals to 8 units in its length, BC equals to 10 units in its length. Actually BC is the diameter of the semicircle, so we know that the diameter of the semicircle is 10, therefore the radius must be equal to half of it. The radius must be equal to 10 over 2, that is 5. So the radius of the semicircle is equal to 5 units in its length. And we also know that this is angle ABC, this is a right angle. So we define the center of this semicircle, this point is point O. The radius of this semicircle is 5. So OB is the radius of the semicircle, that is 5. OC is also the radius of the semicircle, that equals to 5 units in its length. We join points P and O together by a straight line. PO is also the radius of the semicircle, that is equal to 5 units in its length. In the next step, we join points P and B together by a straight line. By doing this construction, we can do peripheral angle BPC. This is peripheral angle BPC that subtends on BC, that is the diameter of the semicircle, and according to rule 5, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this peripheral angle BPC that subtends on BC, that is the diameter of the semicircle, must be equal to 90 degrees in its size. So if we click on rule 5, according to rule 5, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle. This is peripheral angle AEB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle AEB must be equal to 90 degrees in its size according to this rule, rule 5. We have already implemented rule 5 in our drawing. In our drawing, so as I mentioned before, we have peripheral angle BPC that subtends on BC, that is the diameter of this semicircle, and therefore peripheral angle BPC must be equal to 90 degrees in its size according to rule 5. So we know that AC is a straight line. According to what is given as the question, AC is a straight line. So if we focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have in the left side of the straight line AC at point P? We have this angle, that is the right angle, plus this missing angle. In total must be equal to those two angles. In total must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we define angle BAP. This angle is alpha. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. And therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. We know that angle ABC equals to 90 degrees in its size according to what is given as the equation. This is angle ABP that is equal to 90 degrees minus alpha. So the missing angle BPBC must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees. That is the size of the big angle, angle ABC. Therefore, this missing angle must be equal to alpha. So in the right angle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. So in the next step, we'll prove that the right angle BPC, this is the right angle BPC, is similar to the right angle APB. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we found out that all the angles in the right big triangle BPC are correspondingly equal to all the angles of the right small triangle APB. Therefore, those two right angles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle BPC is similar, this is the sign of similar to the small right triangle APB, according to angle similarity rule. Okay, so, and from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right angle APB over side BC of the big right angle BPC is equal to side BP of the right small triangle APB over side PC of this big right triangle PBC. It again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the small right triangle ABP over side BC of the big right triangle BPC is equal to side BP of the small right triangle APB over side PC of the big right triangle BPC. AB is the missing side, so we limit as it is. Over BC. BC is the diameter of the semicircle that is equal to 10 units in its length according to what is given as the question. And it is equal to BP. BP is the missing side, so we leave it as it is. Over PC. PC equals to 8 units in its length. And you can also derive that side AP of this small right triangle APB is equal to side AP of the small right triangle APB over side BP of the big right triangle BPC. So today we found out that from the fact that those two right triangles are similar to each other, the following relationship exists between their sides, that AB over BC equals to BP over PC, and it is equals to AP over BP. BP is a common side that belongs to both triangles. It is very easy to see that BP belongs to the right triangle APB, and BP also belongs to the big right triangle BPC. So we have AP over BP. AP is the missing side, so leave it as it is. Over BP. So in total we found out that AB over 10 equals to BP over 8 equals to AP over BP. So, but before that, we'll implement the Pythagoras theorem on the right triangle BPC in order to find out the missing side PB. So in this right triangle BPC, by PT is a relation for Pythagoras theorem. BC squared, that is the square of the hypotenuse, is equal to BP squared plus PC squared. So repeat again, in this right triangle BPC, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to BP squared plus PC squared. PC is 10, therefore BC squared is 10 squared, that is 100, and it is equals to PB squared. PB is the missing side, so we leave it as it is. So it is PB squared plus PC squared. PC is 8, therefore PC squared is 8 squared, that is 64. So in total we found out that 100 equals to PB squared plus 64. Here we subtract 64 from this equation, and we get that 100 minus 64 is 36, so 36 equals to PB squared. Here we take a root out of this equation and finally find out that PB equals to the square root of 36, that is 6. So PB equals to 6 units in its length. PB equals to 6 units. PB equals to 6 units in its length. So she found out that from the fact that those two right triangles are similar to each other, the following relationship exists between their sides. That AB over 10 equals to BP over 8 equals to AP over BP. So it is AB over 10 is equals to BP over 8. BP is 6. We just right now found out that BP equals to 6 units in its length. So it is 6 over 8. And it is also equals to AP over BP, that is 6. So in total we found out that AB over 10 equals to 6/8 equals to AP over 6. So those two sides are equal to each other, so we get equation 1 from those two sides that are equal to each other. So according to equation 1, we get that AB over 10 is equal to 6/8. Here we multiply this equation by 10, and finally we get that AB equals to AB equals to 10 times 6, that is 60 over 8. So if you found out that AB equals to 60 over 8, AB equals to 60 over 8, here we divide both the numerator and the denominator of this number by 4, and get that 60 over 4 is 15, and 8 over 4 is 2. So in total we should find out that AB is equal to 15 over 2 units in its length. So this is line segment AB is equals to 15 over 2 units in its length. That's actually 7.5 units. Those two expressions are also equal to each other, so we get equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that 6/8 equals to AP over 6. And again, if you found out that according to equation 2, 6/8 equals to AP over 6. Here we multiply the equation 2 by 6, and we get that AP, according to equation 2, AP equals to 6 times 6, that is 36 over 8. So AP equals to 36 over 8. Here we divide both the numerator and the denominator of this number by 4, and we get that 36 over 4 is 9, over 8 over 4 is 2. So in total we should find out that AP equals to 9/2. AP equals to 9/2. So we can write down in the drawing that AP equals to 9/2 units in its length. AP equals to 9/2 units in its length. Okay. So our mission is to find out the area of this vein shape. In order to find out the area of this vein shape, we have to find out the area of this segment BP. This is segment BP. So what is the area of segment BP? From the drawing, it is very easy to see that the area of segment BP is equal to the area of sector PBO minus the area of triangle PBO. Repeat again, the area of segment BP this is segment BP, and from the drawing it is very easy to see that the area of segment BP is equal to the area of sector PBO. This is sector PBO. So this is sector PBO minus the area of this triangle PBO. So minus the area of triangle PBO. PBO. Triangle PBO is an isosceles triangle. Okay, again, the area of this segment BP is equal to the area of sector POB minus the area of this triangle PBO. And the area of segment BP is equal to the area of sector BPO minus this isosceles triangle, PBO. It is an isosceles triangle because side PB equals to side PO equals to 5 units in its length, and BP equals to 6 units in its length, according to what we already found out. But what is a sector? A sector is a portion of a circle enclosed by 2 radii and the arc between them. Again, the green shape ABO, is a sector. Actually, a sector is like a slice of a pizza. And repeat again, this is sector ABO. That is a portion of a circle with 2 radii and the arc that enclosed between the 2 radii. This is the angle theta, that is the angle between the legs of the sector and the 2 radii. And what is the area of this sector AOB? The area of sector AOB is equal to the area of the circle, that is pi r squared, times angle theta over 360 degrees. I repeat again, the area of this sector AOB equals to pi r squared, that is the area of the circle, times theta over 360 degrees. So the area of segment BP will be equal to the area of sector BOP. We know that BO equals to 5, it is the radius of the circle. PO also equals to 5, it is also the radius of the semicircle. And this is angle theta. So in order to find out the value of angle theta, we'll implement the law of cosines in this triangle BPO. Actually, the law of cosines is so in any triangle, therefore we can definitely implement the law of cosines in this triangle BPO. This is triangle BPO. According to the law of cosines, in this triangle BPO, cosine theta is equal to 5 square plus 5 square minus 6 square over 2 times 5 times 5. Okay, again, according to the law of cosines, in triangle PBO, the following equation is true, that cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. 5 square is 25, so 25 plus 5 squared is 25. 25 plus 25 is 50, minus 6 square is 36. And 50 minus 36 is 14, so in the numerator in total we have 14 over 2 times 5 times 5. 5 times 5 is 25, and 25 times 2 is 50. So in total we have found out that cosine theta is equal to 14 over 50. Our task is to find out the value of theta itself. In order to find out the value of theta itself, we will operate the opposite function of cosine on the result, and this will give us the value of theta. The inverse function of cosine is arc cosine. Arc cosine will operate the opposite function on the result, that is 14 over 50. When you operate the opposite function on the result, it will undoes the function of cosine theta itself. Therefore, it will give us in return the value of theta itself. So we operate the opposite function of cosine, that is arc cosine, on the result, that is 14 over 50, and this will undoes the operation of cosine. Therefore, it will give us the value of theta itself. And we know that the arc cosine of 14 over 50 equals to theta, and therefore theta itself will be equal to 73.74 degrees in its size. And again, we found out that theta equals to 73.74 degrees in its size. So this angle theta is equal to 73.74 degrees in its size. So the area of segment BP is equal to the area of sector OBP minus the area of the associated triangle BOP. It again, we have already found out that the area of segment BP is equal to the area of sector BOP minus the area of the associated triangle BPO. We already found out that the area of any sector is equal to pi r squared, that is the area of the circle, times the angle between the legs of the sector, that is actually 73.74 degrees over 360 degrees. R is 5, therefore r squared is 5 squared. In R is 5, there is the radius of the semicircle, that is 5. Therefore r squared is 25, 5 squared, that is 25. So pi r squared is 25 pi times 73.74 over 360 degrees. So the value of this expression, that is to say 25 pi times 73.74 over 360 degrees, is equal in total to 16.088 square units. So we check if I'm not wrong. 25 pi times 73.74 over 360 degrees is actually 16.88 square units. So I should find out that they are on the semicircle is equal to 16.088 square units in its size, minus the area of this associated triangle BPO. Actually, we have the rule that we have, first of all, those are the two equal sides, BO and BPO, and BP is the base of this associated triangle BPO. We have the rule that says that the perpendicular to the base will bisect the base. In any associated triangle, the perpendicular to the base bisects the base. You know that BP in total equals to 6. So the perpendicular, this is the perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BP. This point is point M. Again, according to the rule that I mentioned, the perpendicular OM to the base BP bisects chord BP. BP in total is 6, therefore half of 6 is 3. So MP equals to 3 and BM also equals to 3. So we implement the Pythagoras theorem on this right triangle PMO. According to the Pythagoras theorem, this right triangle PMO, 5 square minus 3 square is equals to MO square. 5 square is 25, minus 3 square is 9, 25 minus 9 is 16. So MO square equals to 16. Here we take out all of this equation and finally get that MO equals to the square root of 16, this is 4. So we found out that MO is equals to 4 units in its length. MO is the height to the base BP. Therefore, in total, the area of this triangle, associated triangle BOP is equal to the base BP times the edge MO over 2. The base BP equals to 6 units in its length times MO, the height MO, that is 4 over 2. So in total, the area of this associated triangle BPO is equals to 6 times 4, that is 24, over 2, that is 12. So in total, we found out that the area of this associated triangle BPO is equals to 12 square units in its length. And the area of segment BP equals to the area of the sector BPO minus the area of this associated triangle BPO. So it is 16.088 minus 12, that is actually 4.088. So in total, we found out that the area of this segment BP is equal to 4.088 square units in its size. And again, the area of this segment BP is equal to 4.088 square units in its size. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total is equal to the area of the right triangle APB minus the area of this segment PB. Again, the area of this green shape must be equal to the area of the right triangle APB minus the area of this segment BP. The area of the green shape equals to the area of the right triangle PAB minus the area of segment BP. The area of this right triangle APB is equals to the base, that is AP, times the height, that is PB, over 2. The base AP is 9 over 2, that is 4.5, times the height PB, that is 6 over 2. 6 times 4.5 is 27, and 27 over 2 is 13.5 square units. So if you found out that the area of triangle PAB is equals to 13.5 square units minus the area of segment BP. The area of segment BP is equals to 4.088 square units. And 14.5 minus 4.088 is equals to 9.412 square units. That is the answer to the question. We actually found out that the area that we are looking for in this question, that is the area of this ring shape, is equal to 9.412 square units. So we finish with the first question. In the next step, I present you the second question, and we solve the second question in two different methods. In the second question, our task is to find out the length of line segment AP that is equal to x. We have to find out the value of x. So, first of all, we know that in the domain we have a semicircle. The diameter of this semicircle AB equals to 10. We know that this is line segment BC that is equals to 6 units in itself. PC equals to PB equals to x, and our task is to find out the length of P8 is equals to x. We have to find out the value of x. So we start with the first method. We define the center of this semicircle. This point is point O. So we know that the diameter of this semicircle is 10. Therefore, the radius must be equal to 10 over 2, that is 5. So OA is the radius of this semicircle, that is 5. OB is also the radius of the semicircle, that is 5. We join points P and O together by straight line. PO is of course the radius of this semicircle, that is 5. Okay. So here we have triangle POA. POA is an isosceles triangle because PO equals to OA equals to 5. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other in their sizes according to the rule that I mentioned. Okay, so in the isosceles triangle PAB, this angle equals to alpha, this angle also equals to alpha. Therefore, this third missing angle must be equal to 180 degrees minus 2 alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. We also know that the big triangle APC is also an isosceles triangle because of the fact that side AP equals to side PC. And according to the same rule that in front of equal sides in the triangle there are equal angles. So in the isosceles triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But this is angle alpha. Therefore, this angle must be also equal to alpha because they must be equal to each other and their sizes according to the rule that I mentioned. Okay, so here in the big isosceles triangle APC, this is angle alpha, this is also angle alpha, and therefore this missing angle must be equal to 180 degrees minus 2 alpha, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. So this missing angle must be equal to 180 degrees minus 2 alpha. So in the next step, we will prove that the small isosceles triangle APB is similar to the big isosceles triangle APC according to angle similarity rule. So I'll copy those two isosceles triangles in a new page and we prove that they are similar to each other. What is the length of side AC? AC in total equals to AB plus BC. That is to say, AC equals to AB, that is 10, plus BC, that is 6. That is 6. So in total, AC equals to 10 plus 6, that is 16. Roughly, those are the two associated triangles that are going from the original domain. So in the next step, we'll prove that those two associated triangles are similar to each other according to an angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. So we can prove that all the angles of the big right triangle of the big associated triangle ABC are correspondingly equal to all the angles of the small associated triangle APO, and therefore those two associated triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big associated triangle APC is similar. This is the sign of similar to the small associated triangle APO according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AC of the big associated triangle APC over side AP of the small associated triangle AOP is equal to side AP. AP is actually a common side that belongs to both triangles. So it is equal to side AP of the big associated triangle APC over side AO of the small associated triangle AOP. So if you take it from the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC of the big associated triangle APC over side AP of the small associated triangle AOP is equal to side AP of the big associated triangle APC over side AO of the small associated triangle AOP. AC is 16. So AP is X here. That is the line segment that we're looking for in this question. So AC is 16 over AP is X, and it equals to AP, that is X, over AO, that is 5. This is the radius of the semicircle, that is 5. So in total, we actually found out that 16 over X equals to X over 5. Here we cross multiply this equation, and we get that X times X is X squared, so X squared equals to 16 times 5. Repeat again, X squared equals to 16 times 5. Here we take a root out of this equation, and finally we get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total we found out that the length, that X equals to either 4 times square root of 5, or in terms of numbers it is actually equals to 8.94 units. So repeat again, according to the first method, we should find out that the length of this line segment AP is equals to X. It is equals to either 5 times square root of 4 times square root of 5 units in its length, or in terms of numbers, the length of this line segment AP is equals to X is equal to 8.94 units. So we finish with the first method. The next step I present to you how to find out the length of this line segment AP is equals to X in a different way. So here we implement the rule that says that the perpendicular to the base of an isosceles triangle bisect the base. And again, we have the rule that states that the perpendicular to the base in an isosceles triangle bisect the base. So we know that APC is an isosceles triangle because AP equals to PC equals to X. The base of this isosceles triangle is of course AC. So from point P, we go perpendicular to the base AC of this isosceles triangle APC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AC. This point is point M. We know that the base AC equals to 10 plus 6, that is 16. AC equals to 16. The base AC equals to 16 units in its length. So according to the rule that I mentioned, the perpendicular PM bisects the base AC. That is to say, it divides it into equal halves. If AC is 16, the first half will be equal to 16 over 2, that is 8. So the first half is AM, that is 8. And the second half is MC, that is also 8. We define the radius of this semicircle as O. We know that the diameter AB is 10, therefore the radius AO is 5. And the radius OB is also 5. So what is the length of OM? OM equals to AM minus AO. Again, OM equals to AM minus AO. So write it down. OM equals to AM minus AO. So OM, the length of this small line segment OM is equal to AM. AM is 10, according to what we already found out just right now. So AM is 10 minus AO, that is 5, this is the radius of the semicircle. So in total, OM equals to 8 minus 5, that is 3. OM equals to 3 units in its length. OM equals to 3 units in its length. In the next step, we join points P and O together by a straight line. Point O is the center of the semicircle, point P is the point of the semicircle itself, therefore PO is the radius of the semicircle, that is equal to 5 units in its length, according to what we have already found out. So, in the right triangle OPM, according to the Pythagoras theorem, so we implement the Pythagoras theorem on this right triangle OPM. So here by PT is the derivation from Pythagoras theorem. So actually, this is the small right triangle OPM, is a copy from the original drawing according to the Pythagoras theorem. In this small right triangle OPM, PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. So write it down. According to the Pythagoras theorem, in this side again POM, PO squared, that is the square of the hypotenuse, is equal to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equal to PM squared. PM is the missing side, so we leave it as it is, plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we have found out that 25 equals to PM squared plus 9. Here we subtract 9 from this equation, and finally we get that 25 minus 9 is 16, so PM squared equals to 16. Here we take a root out of this equation, and finally we get that PM equals to the square root of 16, that is 4. So if you found out that the missing side PM is equal to 4 units in its length. In the next step, we'll implement the Pythagoras theorem on this big right triangle APM. So I copy this right triangle APM in your page, and we'll implement on it the Pythagoras theorem. Actually, the hypotenuse AP equals to x, that is the line segment that we are looking for in this question. AM equals to 8 units in its length, according to what we have already found out, and PM equals to 4. So here by PT is the information for Pythagoras theorem. So here, this is the right triangle APM, that is coming from the original drawing. According to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, equals to PM squared plus AM squared. So I write it down. AP squared, that is the square of the hypotenuse, is equal to PM square plus AM square. AP is x, that is the line segment that we are looking for in this question, so AP square is x square, and it is equal to PM square. PM is 4, therefore PM square is 4 squared, that is 16, plus AM square. AM is 8, therefore AM square is 8 squared, that is 64. So in total, x squared equals to 16 plus 64, that is 80. X squared equals to 80. Here we take a root of this equation, and we get that x equals to the square root of 80. 80 is 16 times 5, therefore we substitute 80 by 16 times 5. Square root of 16 is 4. So inside the root, we left only with 5. So in total, we found out that the length of line segment AB is equal to x. It is equal to either 4 times square root of 5 units in its length, or in terms of numbers, it is equal to 8.94 square units. Exactly the same result as we had in the first method. So in the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task is to find out the area of this green shape. So it is given us in the question that BC equals to 10 units in its length. We know that PC equals to 8 units in its length. And our task is to find out the area of this green shape. So first of all, we define the center of this semicircle. This point is point O. The diameter BC is 10, therefore the radius must be equal to 5. So BO is the radius that is 5, OC is also the radius that is 5, and PO is also 5 because it is the radius. And we join points B and P together by a straight line. By joining points B and P, we get that peripheral angle BPC. Peripheral angle BPC equals to 90 degrees in its size. And we have, according to rule 5, any peripheral angle that is equal to 90 degrees in its... Actually, again, peripheral angle BP subtends on BC, that is the diameter of the semicircle. And according to rule 5, any peripheral angle that subtends on the diameter of the circle or a semicircle must be equal to 90 degrees in its size. Therefore, peripheral angle BPC that subtends on BC, that is the diameter of the semicircle, must be equal to 90 degrees in its size. So in the right angle BPC, this angle equals to 90 degrees. But before that, we know that AC is a straight line. So if we focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AC at point P? We have this angle that is a right angle, plus this angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this angle must be equal to 90 degrees in its size. So in the right triangle APB, we define this angle as alpha. So this angle equals to alpha according to our definition. This angle equals to 90 degrees according to rule 3. Therefore, this third angle must be equal to 90 degrees also alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we know that according to what is given us in the question, this is angle ABC, this is the right angle. So angle ABP is equal to 90 degrees minus alpha. Therefore, this missing angle PBC must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is equal to 90 degrees. That is the size of the big angle ABC. Therefore, this missing angle must be equal to alpha. So with the right angle PBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we prove that the big right angle BPC is similar to the small right angle APB. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the figures of the big right angle BPC are correspondingly equal to all the figures of the small right angle APB. Therefore, those two right angles are similar to each other according to angle similarity rule. So if it again, we should find out that the big right angle BPC is similar to the small right angle APB according to angle similarity rule. And for the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AB of the small right angle ABP over side BC of the big right angle BPC is equal to side BP of the small right angle APB over side PC of the big right angle BPC, and it is also equals to side AP of the small right angle APB over side BP of the big right angle BPC. Actually, side BP is a common side that belongs to both triangles. So we should find out that AB over BC equals to BP over PC equals to AP over BP. AB is the missing side, therefore we leave it as it is. BC is 10, BP is the missing side, so we leave it as it is, or PC is 8. And it is equals to AP over BP. So actually we found out that AB over 10 equals to but we have to find out the length of BP. In order to find out the length of BP, we implemented the Pythagoras theorem on the right triangle BPA. So according to the Pythagoras theorem, BC square, that is the square of the hypotenuse, minus BP, BC square minus PC square equals to BP square. PC is 10, therefore PC square is 10 squared, that is 100, minus PC square. PC is 8, therefore PC square is 8 squared, that is 64. So 100 minus 64 is 36, so BP square equals to 36, therefore BP equals to, we took out of this equation, and finally found out that BP equals to the square root of 36, that is 6, so BP is 6. So here we have AB over 10 equals to BP, that is 6 over 8, and it is equals to AP over BP, and BP is 6. So in total we should find out that AB over 10 equals to 6/8 equals to AP over 6. Those two expressions are equal to each other, therefore we can get equation 1 from those two expressions that are equal to each other. So according to equation 1, AB over 10 equals to, actually those two expressions are equal to each other. So we can get equation 1 from those two expressions that are equal to each other. So according to equation 1, AB over 10 equals to 6/8. AB over 10 equals to 6/8. Here we multiply this equation 1 by 10, and finally found out that AB equals to 10 times 6, that is 60 over 8. Okay, AB equals to 60 over 8. AB equals to 60 over 8. We divided both the numerator and the denominator of this expression by 4, and finally found out that 60 over 4 is 15 and 8 over 4 is 2. So in total we found out that AB equals to 15 halves. So actually those two expressions are also equal to each other. Therefore we can get equation 2 from those two expressions that are equal to each other. So according to equation 2, 6/8 equals to AP over 6. 6/8 equals to AP over 6. Here we multiply this equation by 6 and finally found out that AP equals to 6 times 6, that is 36 over 8. So AP equals to 36 over 8. Here we divided both the numerator and the denominator of this number by 4. And finally found out that 6 over 4 is 9 and 8 over 4 is 2. So in total we found out that AP equals to 9 halves. So we found out that AP equals to 9 halves and AB equals to 15 halves. Okay. So our task is to find out the area of this green shape. In order to find out the area of this green shape, we have to find out the length of the size of segment BP. What is the size of segment BP? From the drawing it is very easy to see that the size of segment BP is equal to the size of sector PBO minus the size of triangle PBO. Again, sector PBO minus triangle PBO is equal to the size of this segment PB. And again, the size of segment PB equals to the size of sector PBO minus the size of triangle PBO, that is an associated triangle. The area of sector POB equals to pi r squared times the angle between the rest of the sector, that is 73.74 over 360 degrees. R is 5, therefore r squared is 25. So in total, the area of this sector is equal to 25 pi times 73.74 over 360 degrees. So in total, we actually found out that the area of this sector equals to 16.088 square units. Minus the area of this associated triangle BPO. Actually, from point O, we go perpendicular on the base PB. And we have the rule that in any associated triangle, the perpendicular to the base bisects the base. The base PB is 6, therefore the perpendicular OM bisects it into 2 halves. Each half equals to 3. So PM equals to 3 and MB equals to 3. So in the right triangle OMB, according to the Pythagoras theorem, 5 square minus 3 square equals to OM square. 5 square is 25, minus 3 square is 9, 25 minus 9 is 16. So MO square equals to 16. We took out all this equation and finally found out that MO equals to 4. So the height to the base PB is 4. Therefore the area of this triangle must be equal to the base PO, that to the base PB, that is 6, times the height OM, that is 4 over 2. So it is 6 times 4 over 2. 6 times 4 is 24, and 24 over 2 is 12. So in total we should find out that the area of this associated triangle POB is equal to 12 square units. So in total, the area of this sector, that is 16.088 minus the area of this triangle, that is 12, is equal to 4.088 square units. So the area of segment BP is equal to 4.088 square units in its size. Our task is to find out the area of the green shape. So the area of the green shape is equal to the area of this green shape is equal to the area of triangle APB minus the area of this segment BP. Repeat again, the area of the green shape is equal to the area of triangle PAB. This is the right triangle PAB minus the area of this segment PB. And this is equal to the area of the right triangle PAB minus the area of segment BP. So what is the area of this triangle PAB? It is equal to the base, that is 4.5, times the height, that is 6 over 2. Or AP times PB over 2. The base AP times the height BP over 2. AP is 4.5, BP is 6 over 2. 6 over 2 is 3, and 3 times 4.5 is 13.5. So in total, if we found out the area of this triangle APB is 14.5 square units, minus the area of this segment BP. We already found out that the area of segment BP is equal to 4.088 square units. So 13.5 minus 4.088 is 9.412 square units. So in total, we found out that the area of the green shape is equal to 9.412 square units. So finish with the first method. Actually, here we have only one method. Actually finished with the first question. In the next step, I presented to the second question and solved the second question in two different methods. Our task in the second question is to find out the length of line segment AP is equal to x. We have to find out the value of x. So in the moment we have a semicircle, and we know that AB, that is the diameter of the semicircle, equals to 10 units in its length. Line segment BC equals to 6 units in its length. Again, our task is to find out the length of AP is equals to x. We have to find out the value of x. So, first of all, we define the center of this semicircle. This point is point O. The diameter is 10, therefore the radius is 5. So, the radius OA is 5, the radius OB is 5, and the radius OP is also 5. So, here we have the associated triangle APC, but we have also the associated triangle APO. Why is triangle APO is an associated triangle? Because AO equals to OP. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other in their sizes. So the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they must be equal to each other. So in triangle APO, this angle is alpha, this angle is alpha, therefore this first missing angle must be equal to 180 degrees minus to alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big associated triangle APC, why triangle APC is an associated triangle? Why triangle APC is an associated triangle? Because AP equals to PC equals to x. In front of those two equal sides, there are those two angles that must be equal to each other in the associated triangle APC. But this is angle alpha, so this angle must be also equal to alpha, because those two angles must be equal to each other according to the rule that I mentioned. So in the next step, so in the big associated triangle APC, those two angles are equal to alpha, therefore this third receding angle must be equal to 180 degrees minus 2 alpha. In the next step, we prove the big associated triangle APC in the small associated triangle APO in a new page, and we prove that those two associated triangles are similar to each other according to angle similarity rule. So the two associated triangles that are going from the original drawing. This is the big associated triangle APC, and this is the small associated triangle APO. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So if you prove that all the figures of the big associated triangle APC are correspondingly equal to all the figures of the small associated triangle APO. And therefore those two associated triangles are similar to each other according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC of the big associated triangle APC over side AP of the small triangle APO of the small associated triangle APO is equal to side AP of the big associated triangle APC over side AO of the small associated triangle APO. So AC over AP equals to AP over AO. AC is 16, AO is X, and AP is X, and it equals to AP, this is X, over AO, that is 5. So in total, we found out that 16 over X equals to X over 5. Here we cross multiply this equation, and finally found out that X squared equals to 16 times 5. Here we took out of this equation, and finally found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total, we found out that X equals to 4 times square root of 5 units in itself. In terms of numbers, AP is equal to X is equal to 8.94 units. So finish with the first method. In the next step, I presented to you a new method, or a second method, to find out the length of this size element AP is equal to X. In the second method, we used the rule that in any associated triangle, the perpendicular to the base bisect the base. So this is associated triangle APC, the perpendicular to the base AC, the perpendicular PM bisect the base AC. AC in total is 16, therefore it bisects the base AC into two halves. Each half must be equal to 8. So AM equals to 8, and MC, the second half, also equals to 8. We define the center of this semicircle as O. The radius, the diameter is 10, therefore the radius must be equal to 5. So AO is 5, OB is also 5, and OP is the radius that is 5. So here we have we know that OM equals to AM minus AO. OM equals to AM over AO. So OM equals to AM, that is 8, minus AO, that is 5. So in total OM equals to 8 minus 5, that is 3. So OM equals to 3 units in its length. The opposite OP equals to 5. That are OPM. And PM is the missing side. So I copied the small right triangle POM in a new page and implemented the Pythagoras theorem on this small right triangle PMO. So actually this is the small right triangle PMO that are going from the original domain only to the Pythagoras theorem. PO squared, that is the square of the product, equals to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, and it is equals to PM squared. PM is the missing side, so we leave this it is. Plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we found out that 25 equals to PM squared plus 9. Here we subtract 9 from this equation and found out that PM squared equals to 25 minus 9 is 16. So PM squared equals to 16. Here we took out of this equation and found out that PM equals to the square root of 16, that is 4. So there is inside PM equals to 4 units in its length. Here PM equals to 4 units in its length. So in the last step, we implemented the Pythagoras theorem on this right triangle APM. So I copied the big right triangle APM in an equation and implemented on it the Pythagoras theorem. So this is the right triangle APM that I copied from the original drawing. AP equals to x, that is the line segment that we're looking for in this question. PM equals to 4 and AM equals to 8. So according to the Pythagoras theorem, in this right triangle APM, AP squared, that is the square of the hypotenuse, equals to PM squared plus AM squared. AP is x, therefore AP squared is x squared, and it equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total we found out that x squared equals to 16 plus 64, that is 80. So x squared equals to 80. Here we took out of this equation and found out that x equals to 80. 80 is 16 times 5, therefore we substitute 80 by 16 times 5. So in total x equals to the square root of 16, that is 4. So inside the root we left only with 5. So in total we found out that x equals to either 4 times square root of 5 units, or in terms of numbers, 8 equals to x equals to 8.94 square, x equals to 8.94 units. I repeat again. According to the second method, we found out that AP is equals to x, it is equals to either 4 times square root of 5 units in its length, or in terms of numbers, AP is equals to x is equal to 8.94 units in its length. So in both methods, we have the same result. Okay, thank you very much.